Hello and welcome to Principles of Mathematics lesson number 22. In this lesson, we're going to learn about repeating decimals. We will learn what repeating decimals are and how some fractions can be converted to repeating decimals and vice versa. We'll learn about ordering repeating decimals, and we'll also learn about a surprising result, which is quite interesting, that zero point 0.9 bar is the same as 1. Now, zero point 0.9 bar being 0.9 and then the 9 continuously repeating indefinitely. So we'll look at that result as well. Now, we've already learned that some decimal numbers like 0.475 can be categorized as what we call terminating decimals, because there comes a point where the decimal simply stops, right? But not all rational numbers can be represented by terminating decimals. For example, if you take 2 over 11 and do a long division, you're going to find that this 0.18 will start continuously repeating. You're going to get the same result over and over again, and this 0.18 repeats. So we write that result in the following way. So we write 0.18, and instead of writing 181818 several times, because we can't write them all because it goes on forever, we just write 0.18 and then we put a bar on the top of the part that repeats, and the part that repeats will be called the repeatend, and the decimal itself will be called a repeating decimal. So once again, a decimal of this type is called a repeating decimal, and the repeating block of digits is the repeatend. The repeating decimal is written in this way with 0.18 bar, where the bar indicates that the block of digits underneath that bar is repeated continuously and indefinitely. A rational number is reduced in reduced form with a prime factor denominator that has no factors other than 2 or 5 can be converted to a terminating decimal. We've already seen that in our previous lesson. Remember, we want no factors other than 2 or 5 in order to be able to write the fraction as a terminating decimal, and we've already accomplished that in our previous lesson. Now, a rational number in reduced form with a prime factor denominator that has factors other than 2 or 5 can be converted to a repeating decimal, the type we're discussing in this lesson. Now that we've learned about repeating decimals, there are some interesting facts that we can state. One is that a rational number of the form a over b is either going to be a terminating decimal, meaning the denominator's prime factorization has no factors other than 2 or 5 in it, or a repeating decimal. The denominator's prime factorization has factors other than 2 and 5 in it. Of course, if the fraction is in simplified form, right? A decimal number that is neither repeating nor terminating is called an irrational number. Now, it's important to understand that the set of real numbers is composed of nothing but these two types of numbers. So if you look at a real number, it's either going to be rational or irrational. The set of rational numbers we've already seen, which we call Q, is basically can be written also in this way. We've already seen this definition for the set of rational numbers. Q is equal to all fractions of the form m over n, such that m and n both belong to the set of integers, and n does not equal to 0. Well, with our new understanding, we can also write the set of rational numbers in this way. The set of all x such that x belongs to the set of real numbers, and x in decimal form is either repeating or terminating. The set of irrational numbers can be written in this way. All x such that x belongs to the set of real numbers, and that x in decimal form is neither repeating nor terminating. Another way that sometimes the set of irrational numbers is referred to is in this manner. P, which is the letter we usually use for it, is all x such that x belongs to R and x does not belong to Q. Because as we said, these two sets are disjoint, they have no numbers in common, and together they form the entire set of real numbers. So if we talk about the numbers in the set of real numbers that do not belong to the set of rational numbers, then you're talking about all the elements of the set of irrational numbers. A very famous example of the set of member of the set of irrational numbers is square root of 2, for example. Okay, it can be shown that the square root of 2 is an irrational number. Here's a visual demonstration of all the sets we've discovered so far. The whole set of real numbers is represented by the largest rectangle here. Within it, we have two disjoint sets, meaning two sets that have no elements in common, the set of rational numbers and the set of irrational numbers. Now, we've already shown that all natural numbers and whole numbers and integers can also be considered rational numbers because they can be written as a fraction where the numerator and denominator are both integers, and also the denominator, of course, can simply be 1, right? So we discovered already that all these elements are also rational. So this is the relationship that we have. Within the set of rational numbers, we have a subset, a proper subset, we call the set of natural numbers. It itself is a proper subset of the set of whole numbers because there's at least one number here that's not in there, namely 0. And of course, both of them exist within the set of integers, which contains not only the natural numbers, but also 0, as well as all the opposites of the natural numbers or whole numbers. So here we have all the familiar sets that we deal with, and then there is this other group, which is in fact larger than this group. Now, you may say, well, they're both an infinite sets, right? So what do you mean by larger? There is actually such a difference between infinities as well. We have levels of infinity, and the infinity associated with the set of irrational numbers is a higher level infinity than the infinity associated with the set of rational numbers. The infinity associated with the set of rational numbers, which is the cardinality of the set of rational numbers, is considered to be aleph 0, whereas the infinity associated with the set of irrational numbers, in other words, the cardinality of the set of irrational numbers, is aleph 1. So a higher level infinity than this one. Now we have this nested relationship of sets, which can also be put in this manner using subset notation. Notice these are proper subset notations. The set of natural numbers is a proper subset of the set of whole numbers, which in turn is a proper subset of the set of integers, which in turn is a proper subset of the set of rational numbers, and finally that is a subset of the set of real numbers. Now, the set of irrational numbers has a lonely relationship here to the set of real numbers. It has no relationship to these other sets. As you can see, these two sets are disjoint. They have no members in common. So the set of rational numbers, however, is a proper subset of the set of real numbers. Now, given the fact that these two sets are disjoint, their intersection is empty, and their union is the entire set of real numbers. Okay, so here we have two rational numbers that we know are not going to be terminating. Why? Because they're simplified and their denominators have factors in other than 2 and 5. So they should be terminating, repeating decimals. Let's take a look. So we divide 1 by 7, and here we can see 0.142857, 142,857, etc. So we write this is equal to 0.142857, and that is precisely the repeatant. So this group of 2, 4, 6 digit will repeat indefinitely. So there is where we're going to put the bar on top of the repeatant. Okay, so let's look at 2 over 13. So we get 0.153846, 153846. So you can see the repeatant is 153846. So we just write it and put a bar on top of it. That means go ahead and repeat that indefinitely. All right, so now we're going to look at a clever way that we can convert a repeating decimal into a fraction of this form. So if we just write that number 0.5, I'm going to write it out a little bit. So instead of using a bar, I'm just going to write it out a little bit. So I know I just get a bunch of 5s, right? All right. Now I notice that if I take this number and multiply it by 10, in other words, if I look at 10n, I'm just going to move the decimal 1 over, right, to the right, and I'm going to end up with 5 point. It's very important that you line this up properly, okay? So mainly your decimal places need to be properly lined up. Then these should line up properly as well. Now watch what happens if I go ahead and subtract these two equations. I get 10n minus n, which is just 9n. And on this side, I get 5 minus 0, which is 5. And what's going to happen to all of these when I subtract? They're all going to zero out, right? So that's it. I get 9n equals 5, and now I can simply divide both sides by 9, and I end up with n equals 5 over 9. So we just converted 0.5 bar into a fraction, and it turned out to be 5/9. Now, this process works in general. If the repeatant appears right after the decimal point, the procedure is simple. You're going to basically want to multiply by a power of 10, which has as many zeros as you have digits that are repeating, right? To be able to accomplish this clever subtraction, right? So for example, let's say we have 0.37 bar, right? Now this time I'm looking at a repeatant with 2 digits, right? So this time I'm going to go ahead and write down the n as 0.37, 37, 37, etc., right? And so instead of multiplying n by 10, as in this case, we're going to multiply by 100, and we end up with 100n equals, notice we're going to move the decimal 2 over. So let me move this a little bit to the left. So we get 37.373737, etc., right? Now when I subtract these two equations, what do I get? 99n equals 37, right? Because the rest of them are all going to zero out when we subtract. So there we have it. So we get n equals, divide both sides by 99, and we get 37 over 99. So again, the process works really simply if the repeatant comes right after the decimal point. Let's see what we have to do if it doesn't. Let's consider this one, right? So here we have n equals, I'm going to write it out a bit because it'll make it easier to understand. So 2.3, and then the 4, 5 keeps repeating, right? Notice that the trick of just multiplying by a 1 and as many zeros as there are here isn't going to work that nicely. However, I noticed that if I just multiply this number by 10, I can get the decimal to move right there to where the repeatant starts, right? So that's what I'm going to do. I'm going to look at 10n which of course becomes this, right? Now, if you notice, these two aren't going to line up nicely, right? So not to worry. What we're going to do is we're going to get clever. So we're going to multiply again, but this time I'm going to want to multiply and move the decimal all the way here, right? So that means I'm going to multiply by 1,000. So because I need to move it 3 places. So I'm also going to look at 1,000n. Notice that 1,000n is going to be 2, 3, 4, 5 point, and then 4, 5, 4, 5, 4, 5, right? So it's going to be, again, I always have to move this a little bit. Okay. So 1,000n is going to be, you got to make sure you line this up correctly. So 2, 3, 4, 5, and then 0.45, 45, 45. Now we have the scenario that we want, right? So now notice that if I subtract, I get 1,000 minus 10, which is 990. So I get 990 n equals, and on this side I get 3 from 5 is 2, 2 from 4 is 2, 23, 22. Notice that all these rest of the digits after decimal are going to zero out after the decimal. So we end up with n equals, divide both sides by 990. So we get 2322 over 990. So remember, we have to just get a little clever when the repeatant doesn't come right after the decimal. So we want to create a scenario with 2 multiplications where we do end up with the repeatant ending up right after the decimals for those 2 multiples. Now, I do always want to give my answer in simplest form, so you can either do that manually, but for the sake of time, I'm going to go ahead and use a calculator to do it. So 2322 divided by 990. When I hit enter, it's going to give me a decimal. So I'm going to, of course, we knew it is, right? So now I'm just going to hit the A and B over C. So I get that. So I get 129 over 55. So there is my 2.345 bar written in fractional form. All right, so that's how we handle those. All right, here's a result that's actually quite interesting. Now, that's a really simple one, right? Because there's only 1 digit to the right of the decimal. But watch what happens. So you know what we have to do. We just have to look at n, which is 0.9999, etc., right? And then since there's only the digit that repeats, the repeatant is right after the decimal, and there's only 1 digit, so we just need 10n, right? You should be able to do this without looking, right? Hopefully you've done that already. All right, so we get what? We just move the decimal 1 over, right? So we get 9.9999, etc., right? So now we're going to subtract. So what's 10n minus n? That's 9n. And on the right side, we have 9, right? Because 9 minus 0 is 9, and these all zero out. So we end up with n equals 1. So if you have 0.99999 forever, that's numerically indistinguishable from 1 as far as value is concerned. Now, even on a calculator, obviously on a calculator, you can't put 9 forever. But if I just notice that if we're saying that 0.9 bar equals 1, then if I subtract 0.9 bar from both sides, I end up with 0 equals 1 minus 0.9 bar, right? So watch, if I just type 1 minus point. Now, I know I can't put infinitely many of them, but I can put a bunch, right? I'll just put it as many as I can that I can fit on the screen, right? That's still quite interesting. So watch, even if I put that, it's still going to give me, it's going to turn that 0.9999 into 1, and it's going to give me 0. So there's another way you can see that the two numbers are the same. All right, now we want to look at ordering repeating decimals. Well, we do it in exactly the same way that we did it for terminating decimals. Remember, we want to write them out. Of course, in this case, you want to definitely expand the bar at least a few times, right? And put them one under the other, right? So here we have 1.3478 with a repeatant of 3.78. So it's 1.3478, 3478, etc., right? So I line this one up right underneath, and I put 1 point. Notice that in this one, the repeatant is the 7821. So I get 1.347, 7821, and then 7821, etc., right? So I repeat the 7821. So now I start scanning from left to right, and I notice the same. That's the first place. This right here is the first spot that there is a difference between them. So right there, as soon as I see the larger digit, I know that I'm looking at the larger number. Remember, the other digits are so much smaller than these that they don't make a difference, right? Even if this one had all 9s here, this would still be the larger number, okay? All right, so that's how you do it, just like we did with terminating decimals. All right, in our last example of this lesson, which is probably our shortest lesson so far, you're probably thinking, yes. All right, we're going to find the rational number in decimal form between these two numbers. So remember, the trick is to write them out a few times. So here we're going to repeat the 35, so 0.353535, etc. And here we're going to repeat 351, so we get 0.351, 351, etc. You can see that the larger number is going to be the one on the top, right? The 0.35 bar. And of course, you can get a number between them very easily, right? So we have 0.351. How about 0.352? That would work, right? How about 0.351 and any digit after 1? All those would be numbers that are between these two numbers, right? Like 0.3514. In fact, 0.3515 with the 15 repeating. All these numbers would be between these two numbers. All right, and there are basically infinitely many of them. And we've already shown in the last lecture that given any two distinct rational numbers, we can easily find infinitely many rational numbers between those two distinct rational numbers by just continuing to find what? the average between the first one and the second one, and then the first one and the average, and then the first one and the new average, and then the first one and the new average, etc. So that's that. All right, so this is pretty much it for this lesson. It's a short lesson. We're going to take a look at a few homework problems and call it the day. All right, just a hint on this one. You're trying to order these. Firstly, just write each one out a few times, right? If it has a repeatant. If it doesn't, obviously you don't, but if it does, write it out. Line them all up nicely, so that maybe even put separators between them so that you can see you're putting the right thing in the right order. And also remember, these are negatives. So with negatives, the larger that part is without the negative, in other words, the absolute value, the smaller the number is. Keep that in mind, okay? All right, for this problem, I want to remind you that we're looking for the sum of the finite geometric sequence whose first term is 1.6, ratio is 0.5, and has 6 terms. So the way that sum works is the following. We're looking for a sum of a series of this type where we have a first term. Remember, geometric series are not like arithmetic series where you just add to each term to get the next term. You multiply by what's called the common ratio, right? So the next one will be the first term times r squared plus a1 r cubed, etc., plus dot 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 plus a1 r to the n minus 1. We have to go to n minus 1 because remember the first one didn't have an r in it, so here in this way we've represented actually n terms, and we call this Sn, right? So the sum of the first n terms of such a sequence. If you remember from when we saw this before, this actually turns out to be a1 times 1 minus r to the n over 1 minus r. So here we know a1. You just have to plug in. Its first term is 1.6. The ratio, the common ratio, is 0.5. And we have 6 terms, so that's going to be n. Now we just have to plug in. So a1 is 1.6 times 1 minus r, which is 0.5, to the power of n, which is 6, over 1 minus r, which is 0.5. And if we work that out on a calculator, we'll see what we get. Okay, so we have, I'm going to use parentheses for my numerator, 1.6, and then I'm going to use another parentheses to show my 1 minus 0.5 to the power of 6. Now I'm going to exit the numerator, and so hit the arrow key, right arrow key twice, and now we're going to put over 1 minus 0.5, and we hit enter. Okay, and that's where we get our results. So 3.15. Okay, let's go ahead and look at another example. All right, here's a clever one. We have 0.235 with a bar on top, so the repeatant is 0.235, so 0 0.235, 235, 235, etc., right, wherever. And then we have 0.2356 2, 3, 5, 6. The question is that if we were to add these two, where do we expect, how many places do we expect the repeatant of the sum of the two decimals to have? If you think about it, basically this is going to be an LCM problem, right? So if you find the LCM, the least common multiple of 3 and 4, you get 12. So by the time you get to 12, they should start repeating. Okay, so basically a problem from the past coming up to visit us. Okay, so look for the LCM of the two. Now write it out a few times, try it. There's nothing better than just writing it out and trying, and then it'll hit you. Oh, this is why it would be 12. Okay, so try it out for yourself. All right, here's a good check on whether you understand the concept or not, because here they're not giving you the digits. They're just telling you, giving you a number which has a repeatant of 3 digits, and the digits are ABC. You want to write this as a fraction. You treat it no differently as if it were 0.234, for example. What would you do if it were 0.234? You would want to multiply by 1,000, right? Remember, multiply by a power of 10 that has as many zeros as the repeatant when the repeatant starts right after the decimal. So we start with 1,000 n, and that's going to be, notice that's going to move the decimal 3 places over. And remember, we're looking at this number, right? The original number is 0.ABC, ABC, ABC. So what happens? It moves 3 over here, it goes there. So it becomes ABC point ABC, ABC, etc., right? On and on. Now, n itself is 0.ABC, ABC, on and on forever, right? So now we subtract 1,000 minus 1 is 999 n is equal to, here 0 from ABC is just going to be ABC, and notice all these others are going to cancel out, right? So now we divide both sides by 999, and what do we get? N is equal to ABC over 999. No different than if you had just 3 regular numbers underneath. Okay? Okay, here we have one where we're going to use the fact that 0.1 bar equals 1/9, 0.01 bar equals 1 over 99, and 0.001 bar equals 1 over 999. Now, these 3 are easy facts you could easily come up with yourself, right? So what we're going to do is use these facts to convert these into fractions. So we don't want to do them from scratch the way we know how, but we want to use these facts. So for example, for part A, we have 0.8 bar. So this is where you have to realize that that's nothing but 8 times 0.1 bar. Think about it, right? If you multiply 8 times 0.1, what do you get? You get, let's look at a calculator real quickly to convince you. So if you look at 8 times 0.1, you end up with 0.8. What if you multiply 8 times 0.11? What do you think you're going to get? Yeah, 0.88, right? What if you multiply 8 by 0.111? You're going to get that, right? Notice, so if you multiply 8 by 0.1 bar, you're going to get 0.888888, which is exactly 0.8 bar. So now we know that 0.1 bar is 1/9. That's given. So we're just going to go 8 times 1/9, which is 8/9, right? For part B, it works very similarly. We have 0.40 bar. Now, it may be a little harder to see for you, but 0.40 bar is 40 times 0.01 bar. Now think about it. Now when you take 40 and multiply it, say, by 0.01, just 0.01, what do you get? You get 40 times 1 over 100, right? Which is 40 over 100, which is what? Which is 0.40. You get it? So in the same way, if you repeat the 01 again, you're going to get another 40. If you repeat it again, another 40. So you can also see that on a calculator. See, if you multiply 40 by 0.01, you get that, which is, now it just shows 0.4, but you can always think of it as 0.40, right? Now multiply 40 by 0.0101, right? What do you end up with? 0.4040. If you would like to add a zero, you can always do that, right? Now multiply 40 by 0.0101. You see that? Again, so this pattern will continue. All right, so basically now we know what 0.01 bar is. It's 1 over 99. So we multiply this by 1 over 99 and we end up with 40 over 99. Okay, next one exactly the same way. I'll let you finish it. Let's look at something else. All right, so we have some addition problems are easier to compute with fractions and some are easier to do with decimals. For example, 1/7 plus 5/7 is easier to compute in fractional form than their equivalents. You know, the equivalents of these are non-terminal, repeating decimals, right? So, and on the other hand, 0.4 plus 0.25 is easier to calculate than this sum in fractional form, right? What situations basically do you think one would be beneficial or the other? Clearly, if you look at it, when the denominators are the same, it's easier to handle it in what? In fractional form. Now, if the denominators are different, it's not necessarily easier to handle it as decimals. It's easier to handle it as decimals if they're nice denominators, meaning what? Meaning the denominators only have powers, only in factored form, only have 2's and 5's in their factorization, and therefore become what? Terminating decimals. See, both of these are terminating decimals. That's when it would be easier to use the decimal form. All right, so here we want to find the number to add to negative 0.023 to obtain a sum greater than 3 but less than 4. So this can be handled extremely easily with a touch of algebra. So what we're going to do is we're going to call the number x. Okay, so basically x, let's start with negative 0.023. We're going to add x to it, right? So negative 0.023, we're going to add the number, and we want this sum to be less than 4, but at the same time greater than 3. So we set up an inequality like that. This is a form of compound inequality. It's really two inequalities lumped into one. It's this inequality, 3 less than negative 0.023 plus x, and this other inequality, negative 0.023 plus x less than 4. So two inequalities kind of lumped into one. It's an AND statement, right? So it's a conjunction. Now the reason we like to write them like this, because when you try to solve either inequality, right, they involve the same steps. So we like to just solve them simultaneously together. So here we're going to go ahead and isolate the x, so that means we're going to add 0.023 to all three parts of this three-part inequality. Sometimes these inequalities are called three-part inequalities. So let's go ahead and do that. So we're going to add 0.023 and we end up with 3.023 less than x less than 4.023. Okay, so let me show you the kind of answers they're going to offer you. Now you're simply going to pick one of those answers that fits this bill. See, you want the number to be between 3.023 and 4.023. And if you look, the only one that satisfies that is the 3.197. So that's how you approach these, and that's how you get them done. Okay? Just wanted to give you an example to get you rolling. Now, all of them are going to be very similar. You just have to kind of like handle each situation based on whether it's an addition, subtraction, etc. But very, very similar. All right, so I think that's a good place for us to call it the day. That should do it for this lesson. Take care, and we'll see you for the next lesson.